The investigations of this video is part of a nice weather station project that will be explained step by step in later episodes. Today we concentrate on a solar generator for an outdoor sensor. The outdoor unit consists out of a sensor, a LoRa transceiver, a charge converter, a lithium-ion battery and of course a solar panel. This is the principle and the components that we are talking about today. But before we buy something, we want to know what size of battery and solar panel would be sufficient. While digging a bit deeper here, we find that countries are very different and weather conditions are can be very specific. On top of this, we are facing very often non-ideal conditions. In other words, the sun can be shaded for several hours per day on our site. How can we tackle this? Now, instead of riding this problem horse to death, we go directly to our spreadsheet tool that you will find in the download section. And we will see what it can do. You can use the spreadsheet in one window. However, I'm using 3 windows of the same spreadsheet. That makes it a bit easier for me to explain really what happens during the simulation. We start with the information about the small solar panel that we have in mind. It has a nominal voltage of 5 volt. The maximum current should be about 125 milliamperes and the total active solar area is 44 centimeters square. These values can be measured with a simple multimeter. Next you get a rating of your solar panel on the middle section here. It gives you the estimated peak power and a comparison to a good reference. Next we need our country conditions. If you search the internet for the so-called monthly yield in kilowatt hours per kilowatt peak, then you will find plenty of information about your location and the solar conditions. Once you filled this in, you get immediately the graphical representation over the year in the middle section here. Now we need to talk about shading from obstacles. The yellow figure here shall help you a bit on how to estimate your non-shaded area. In our example, the non-shaded area is only 72% from the total available 100% of the day's sun. In other words, you cannot use 28% because of obstacles shading. This is given here in the middle section. Next, we have to estimate the efficiency of our charge converter. In our case, it is a linear converter and we cannot expect much more efficiency than 80% here. In the middle section you will find a converter rating that is saying 125 milliwatts as a maximum loss. In case you get higher ratings here, you might want to use this value to dimension a heatsink for the converter. The coming part asks for battery information now. Our lithium-ion battery has a nominal voltage of 3.7 volts and a capacity of about 3000 milliampere hours. Furthermore, we need to tell an initial battery charge, which can be anything between 0 and the capacity of the battery. The internal discharge is given by the supplier. In our case here, 1500 milliampere hours per year means practically that after 1 year there is still 50% of the charge available. The battery rating in the middle section tells you now that you have round about 11,000 milliwatt hours and an internal discharge of about 148 microamperes. Holy moly, this is a bit more complicated than I thought. But congratulations if you made it up to here. We are almost done. What's left is the consumer's information. We have a microprocessor board that is consuming about 50 milliamps in the normal active mode. I skip the sleep mode for the moment and I'm going directly to the transceiver, which is consuming additionally 80 milliamps when it is active. And then we are defining the time period for how long the microprocessor and the transceiver can be active. This is typically something you define in your code. And then we tell how often per hour this arrangement is switched on. We have now a microprocessor board that is roundabout active for 20 seconds per hour. In the middle section you get now the consumer ratings of all kinds you might think of, and I leave you alone with that and the tool, and you can study this on your own. If we look to the right window, everything seems to be okay so far with our energy budgets. The charge flow is always positive and the battery state of charge is fully charged over the whole year. Now here comes the thing. We go back to our sleep mode consumption and insert the value here. In our example, the value is 6 milliamperes. Now I must admit that there is boards out there that are much better. They consume in sleep mode only 400 microampere and less. This would be more than 10 times better than the given board here, but nevertheless we go ahead because it's interesting to see what happens. There will be a part 2 of this video, and low power boards will be subject to it. Coming back to our problem, our power budgets in the right window are showing us that we would be okay in the summer. There is always a positive energy flow. However, it seems that there is no chance to overcome the winter season with it. What can we do now? Increase the battery? We can simulate now that with about 10,000 milliampere hours we would be okay for the winter. However, strong batteries are typically expensive and obviously big. Let's see whether we have better options. Our solar panel is relatively small, with only 44 centimeters square. What if we just use 2 of these relatively inexpensive panels? This would double the maximum current and of course the panel area. Now the problem seems to be solved. What are the learnings of this part? The local conditions are important, And the winter is always critical. With the given spreadsheet tool, you can find a good balance between the battery size and the solar panel. I hope you enjoyed the part 1 and see you for part 2 that will cover a lot more interesting topics in that matter. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.